I will begin, to get up here, with a word of prayer. Heavenly Father, we thank you for this day. Again, I thank you for the students in this class. Just ask you to just be glorify what we do and understand that we'd understand a little more about submanifolds and all these things, Lord, today. In your name I pray, Lord Jesus. Amen. All right, so let me get into it. So I'm trying to just basically, we're covering chapters 4 and 5 of John Lee's book somewhat lightly, but not, make sure I hit the high points here so that at least we know. We'll probably end up running into things later where we need to refer back to these things, so we should at least talk about it a little bit. So to get us started, if we have a smooth mapping from a manifold M to a manifold N, remember, it's said to be a smooth submersion if the differential is surjective, if it's onto at each point in M. And it's said to be a smooth immersion if the differential is injective, right? So, trying to remember what else we said here. I guess that's pretty much it to start with. Now, and I talked a little bit about like the inverse function theorem for manifolds last time, right? So, moving on here. Of course, there's a lot more you could say about local diffeomorphisms. Like there's this theorem, proposition 4.6 has got this like laundry list of all these cool properties of local diffeomorphisms. Be good to read that, of course. Proposition 4.8 says that you have M and M smooth manifolds with or without boundary rather. And if you've got a map from M to N, then it's a local diffeomorphism if and only if it's both a smooth immersion and a smooth submersion. And then if the dimension of M and N is equal, then F is either a smooth immersion or a smooth submersion. If it's either one, then it's a local diffeomorphism. I think I talked about that last time, actually. So that brings me to the rank theorem, which I'm going to write out here. Because this one tends to get used in proofs later, so it's important to kind of know about it. Rank theorem. And maybe I'll talk about this from a linear algebra perspective in here today. Let's see. Let me get it out of my system here. So suppose M and M are smooth manifolds. Of dimension M and N respective. All right. And we've got F, a smooth map from M to N with constant rank R. And so what that means is that the rank of the differential at P of F is equal to R for all P in M, right? What's the rank of the differential? That's the dimension of the image of the differential at each point. Or if we were to choose a coordinate system, it would be the dimension of the column space of the matrix which represents the differential, namely the Jacobian matrix. So there's that. Then for each P in M, there exist smooth charts U phi for M centered at P, and smooth chart V comma psi centered of N centered at F of P, all right, such that the image of U under F is a subset of V, all right, and the local coordinate representative of the map in this context, F hat, all right, of x1 xr plus 1 xm is equal to x1 dot 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 xr, and then zeros. In particular, so, okay, so that's, now what was f hat? We've talked about this a number of times, but maybe I should just put it up there again, right? So a picture is, here's your m, here's your n, we've got u here, we've got v over here, f goes like so. You got your coordinate chart phi here, coordinate chart psi here, and down here we're looking at rm, down here we're looking at rn, and this is f hat, the local coordinate representative, which in particular is given to us by what? Psi composed with f, composed with phi inverse, right? That's the f hat. So f hat is itself a mapping from Rm to Rn. Yep.
You said phi inverse, but then you wrote phi hat.
Oh, goodness gracious. Thank you. Oh, it could be worse. Yesterday I left my backpack in my office. I got done shopping at Walmart. I'm like, someone stole my backpack. What? And then my son is like, why didn't they steal my laptop? I'm like, okay, you've got a point there. And then he posited that my laptop was in my backpack was in my office, and he was right. Go figure, yeah. And then, okay, so now whenever we write this kind of thing, right, this is engaging in the usual identification which John Lee's book makes, right, which is that he's using x's, right, for the, well, I guess the thing is, like, I like to use x's for the manifold coordinates, and he likes to use x's for, these are Cartesian coordinates down on Rm, but he identifies them with the manifold coordinates, is what he says, and he makes that precise, right? Okay, anyway, so that's it. And then if f is a smooth submersion, what's that look like? I'm just going to say s sub merge. All right, then fill in the blank. If f is smooth immersion, then fill in the blank. All right, so then f hat of x1 dot 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 x n xn plus 1 xm is literally equal to x1 xn, no zeros, right? And likewise, in the case it's a smooth immersion, again no zeros, but, oh, excuse me, my bad, lots of zeros. x1, the difference is that it uses all of the x's going in. All right. Now this is the rank theorem. Now, do you guys recognize this theorem from linear algebra? Maybe not, right? So I think if you have never seen this theorem proved in linear algebra, then maybe that's where we should start, all right? Because essentially, the proof which is given in John Lee's is probably more or less an abstraction of that proof, right? So if you don't know the basic proof, maybe we should start there. Also, I know how to prove that part. So I can prove the basic proof. All right, so let's do that. Okay, so we will, content ourselves to look at f going from a vector space V to a vector space W. And I guess our V will be, I'll stick with the counting, right? So my m dimensional and n dimensional, right? All right. And in this context, we have theorems, right? Like, let's see here. So if we're thinking finite dimensional, right? So V is literally the span of, let's say V1 VM, right? That's the basis for F. Let me not do that, actually. I take it back. Sorry. I have to start right. So the thing is, the key idea here is that there's part of F, like there's two things going on, right? F of V, which is also called the image of F, right? That is a subspace of W, right? In this case, the dimension of the image of F is called the rank of F. It's the dimension of the image, all right? And that's going to be less than or equal to the dimension of W, which in this case is N, right? On the other hand, there's also something else going on here which we could talk about, which is the kernel. The kernel of F, which is by definition X in V, such that F of X is equal to 0. That's a subspace of V, right? And its dimension is at most what? What's the dimension of the kernel called? It's called the nullity. The nullity of F is, of course, less than or equal to M, right? If the nullity of F is equal to M, it's the 0 map, which is especially silly, right? Okay, great. Now, so here's the argument. The kernel is a subspace, all right? And as such, we can, let me see here, if I can remember my proof.
Plus the kernel of the whole operating system.
Now you're making operating system kernel jokes.
Yes.
I forbid it. Don't bring your nerdity into this class. This is a math class. This is serious business. There's no space for architecture kernel jokes.
What about the flying spheres that change colors?
Whenever I think of kernel, though, I always think of this classic Monty Python sketch where the mafia is going to the army and going, nice bunch of tanks you've got there, Colonel. Be a shame if something happened to them, wouldn't it? So I love that sketch. It's kind of like the federal government trying to say something to Google as if they have any control. It's hilarious. Or sad, I don't know. No, Google's wonderful. We love Google. So nothing to fear about Google. It's not like they could ruin you.
I mean, they definitely have the power over Google. They just don't know how to use it.
We love Google.
Oh, we love, yeah. I mean, who does?
We love YouTube.
Oh, yeah, YouTube. Who does YouTube own? Who owns YouTube? Oh, wait a minute. Yeah. Oops. All right. So the larger point here is you can. I'll get this eventually. So what I don't want to belabor is the fact that the dimension of the dimension of the kernel plus the dimension of the image, all right, the sum of the dimension of the rank and the nullity has to be M, all right? So that's the way this all works. So I guess I will take the basis. Yeah?
You said it has to be M or N?
It has to be M. Okay. So you know what? I was wrong. I'm going to circle back. So let beta, to start with, equal to v1 vm, a basis for v. All right. Start with that one, and notice that f of beta, which is what, f of v1 f of vm, right? Well, that I don't know if that's a basis or not, but it's definitely a what? Is a generating set. For the image of f, all right? So any vector in the image, I can build from a linear combination of these guys, right? Okay, so then Let's see here. Okay, so then, and I'm sorry guys, I may not be giving you the absolute like slickest proof at the moment. I'm just trying to find a proof to share with you. So if that's a generating set, then I can pick a subset. All right, I can pick a subset of those vectors which will form a basis for the image. Okay, so like without loss of generality, possibly relabeling. All right. Let's let let's suppose that f of v1 f of v, and let's call the rank of f the same as in our theorem. The rank was r. Okay, so let's f of v1 through vr be linearly independent, spanning set for the image of f. Right? Okay. So it follows then, all right, that in this nomenclature, then like v r plus 1 and so forth, all the way until I get to v. How many r is there for v? M must be in the kernel of f. All right. And so, what does this all mean? So the way to be more systematic and like completely logical about this proof is like begin with the this is how I usually prove it. Begin with the basis for the kernel, all right, and then extend the basis for the kernel to the rest of the domain, the rest of V. You can then prove that everything outside of the kernel and that extended basis is necessarily forming the image. You can prove this, and then of course then you can use those as a basis for the image, right? Okay, so then anyway, let me get to it here. So what we're going to do is let's let beta equal to v1 vr plus 1. I don't know why I'm really separating those. It's just, so I'm again letting beta be that basis, but keep in mind I've renumbered them in such a way that the last m minus r of them maps to 0. All right. So like f of vi equals to 0 for I greater than or equal to r plus 1. Okay. And then we need to pick a basis for w. All right. And the basis for w we're going to pick is, guess what? We're going to pick f of v1 and all the way on out to f of vr. All right. The span of those gives you the image. All right. But fun fact, in linear algebra, if you have a linearly independent subset of a vector space, you can adjoin other vectors outside the span of that to get a basis for the whole space. All right. So we just throw in the rest of them. W r plus 1 w n, I guess. Right? So basically I'm saying let w1 be f of v1 and so forth. All right? So like think of this as w1, think of this as wr. All right? Okay, so then if we want to, we can look at the problem like this. We've got vector space V, we've got vector space W, we've got a map that goes from F to W, we can construct coordinate maps in my usual lingo, phi beta, phi gamma, all right? So in linear algebra, I make explicit reference to the basis to tell you which coordinate map you're using, right? We don't do that in manifold theory because our coordinate maps are like way more sophisticated than that, yeah? But anyway, same basic setup, right? Same basic idea. Really, manifold theory, a lot of it is just doing linear algebra in a curved setting, truth be told. So what is f hat here? F hat should be, like phi gamma composed with f, composed with phi beta inverse, right? So let me work on that. What's f hat of like let's see, what's f hat of e sub I? Do you guys remember how the coordinate map is defined in linear algebra? So the way it works is phi beta of vi is equal to ei. What's that?
It's 0.
Oh, not 0. No. Good guess, though. Good guess. Not a bad guess, but let's work through it. Phi gamma of f of phi beta inverse of ei. Okay, so what is phi beta inverse of ei? So if this is the definition of the coordinate map is that it converts the basis, the abstract basis, to the standard basis. That's how we define coordinate map. So this is vi. Right. So we have phi gamma of f of vi, right? But f of vi by construction was what? wi, right? And how does this thing work? Right, so like this has got basis vi up here, I got basis wi over here, and so like phi gamma of wi is equal to, let us call it e bar I, just to emphasize that this is an element of Rn, all right, whereas this was an element of Rm. Okay, so this is straight up e bar I. Yep. And oh, you're right, Jeff. You could have been right. I didn't give you the context. What was you should have been right, but I'm supposing here. Yeah, good. So I shouldn't have said you're wrong. I should have said, well, maybe you're wrong. Or maybe you're right? Because if I wasn't in this context, right? But if I is greater than or equal to, well, let's say it this way: r plus 1 less than or equal to I, less than or equal to m, then you're exactly right. F hat of ei is what? Yeah, I guess is that already clear? Phi gamma of f of vi, but these vi's I claimed were in the kernel, all right? So a little gap in my proof at the moment, but yeah, those are 0. So what is the formula for f hat then?
It's going to be a big bracket.
So like if I use x1 xm for the input, like I think I was over there. Oh, xr, right? R. Xr plus 1 xm. it is equal to, well, I mean, this is linear, right? So this is like literally the sum I equals 1 to, r of x upper I f hat of ei, right? Plus the things that are 0. But that is nothing more than, x1 dot 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 x xr. But the context here is that this is inside where this is a these output the e bar i's, which are actually elements of Rn. So I'm talking about an n tuple, right? So I keep adding zeros past that point, like that. When I teach linear algebra, I present it like this. I say, you can choose a basis for the domain and a basis for the codomain such that the matrix of the linear map has the following form: an identity matrix padded with zeros. So if you watch me teach linear algebra, you'll see that. And this is the R by R identity matrix. So in linear algebra, because you can, if you can adjust the domain and the codomain separately, you can straighten the coordinates essentially by choosing a basis for the codomain, which just makes the output be the basis for the basis in, basis out. And in so doing, that makes the formula for the coordinate representative of the linear map simply this. So what the rank theorem is saying in manifold theory is it's possible to localize this result and to choose charts that make this happen not at just one point, but by at a whole series of points on the manifold. And the proof is about a page and a half long, and it's in John Lee, and I'm lazy. I'm too lazy to prove it in here. So I'm sorry, I'm so lazy. But if you didn't see that in linear algebra, it's probably good for us to look at it together. And if you grad school, at some point in grad school you should prove it for yourself. Okay. All right, so let's go on here. So next up, we had the following corollary. Corollary 413. Let M and N be smooth manifolds. F from M to N is smooth map. Suppose M is connected, then the following are equivalent. For each P in the manifold, there exist smooth charts containing P and F of P, in which the coordinate representation of F is linear, and F has constant rank. Oh, interesting. So that's pretty cool. So if you can, fine. If your local coordinate representative has the form that's given in this theorem, that means that, this means f hat's linear. This formula is manifest linearity of f hat. That's what the formula is. In fact, it's more than it just being linear. It's like stupidly linear, right? Like, what's the matrix for this? Like I just told you, it's the identity matrix padded with zeros. Like, it's not just a linear map. It's like the easiest, one of the easiest ones you can think of. But so if it's, so this is the corollary is turning it around. It's saying that if at each point you can find a chart that makes the local coordinate representative linear, then that means that it has constant rank. If you can do that at each point. Although it's important that M is connected, because the connectivity of M, so like the fact that M is connected means that if you can do this at on one coordinate chart, then like the rank that you're finding is connected to the next one over by like the overlap functions. So you're going to be forced to have the same rank over the whole thing as long as the manifold's connected. See, if it wasn't connected, you could have the situation where the map is like one rank on one part and a different rank on the other disconnected piece. So then he states the global rank theorem. Global rank theorem says M and M smooth manifolds suppose F is a smooth map of constant rank. F is surjective. If F is surjective, it's a smooth submersion. If F is injective, then it's a smooth immersion. If F is bijective, then it's a diffeomorphism. So basically, smoothness of the map overall and global surjectivity or global injectivity implies the smooth. Like, I think of the smooth submersion and smooth immersion properties in some senses like, I guess I shouldn't say they're local properties because that's not quite accurate. It's true for all P and M, right? So are they really local properties? Maybe that's a wrong idea on my part. Yeah, let me shut up about that. Anyway, global rank theorem says what it says. All right, so move on here. Another kind of mapping which is important is a smooth embedding. All right, so let me put that up here. Was it? Oh no. I'm going to have to write it into the syllabus. No non-math pun jokes in my classes. It is forbidden. Just punt them to the next class. I think that makes it worse. I don't know. Let's see here. So if you have M and N smooth manifolds without boundary, a smooth embedding. A smooth embedding of M into N, all right, is a smooth immersion. All right, a smooth immersion I lost my place. Smooth immersion F from M to N, all right, that is also a topological embedding. Topological embedding. And what that actually means is that F of M is a subset of N. That's not really it, though. Golly. Which means that let me just call it F bar for the sake of whatever. He doesn't even write it down. So this is a homeomorphism. What's a homeomorphism? Homeomorphism is a continuous map with continuous inverse, all right? So we're talking about the topology then of the image, all right? And the fine print here is that the image, and this is kind of the important part in terms of the topological commentary here, which is that this is, given the so-called subspace topology. With respect to N. In other words, the image of M under F, the sets which are open in there are obtained by intersection with open sets in N. It's that subspace topology thing I talked to you guys about the other day, that idea. Now, all right, a smooth embedding is a map that's both a topological embedding and a smooth immersion. All right, and then he says not just a topological embedding that happens to be smooth. So, all right. So a smooth immersion. So remember, smooth immersion means the differential is injective at every point in M. Okay. I suppose you could have a map which was smooth and yet not having a injective differential at every point. Then you'd have a smooth map, right? You could have a smooth map which didn't have this condition here, all right? And yet somehow it was a homeomorphism onto its image. Then that wouldn't be a smooth embedding. It would be something else. All right. So what are examples of smooth embeddings? So example 1, if you just have like U, a open subset of a manifold, you can look at my favorite map, right? The inclusion map, the Yoda. That's a smooth embedding. Okay, that's a smooth embedding. Because the differential to the inclusion map, right? What's the what's the rank of that? It's the rank is the dimension of M itself. I mean, all right. So, wait a minute. Wouldn't that make? Oh, right. This is what I wish I had kept from last week. We had a comment like so immersion means the rank. What was it? The rank of the differential P at F is equal to the dimension of M, right? And the submersion would be if the rank of the differential of F was equal to the dimension of N, right? Remember that?
Yeah.
Okay. So since that is a smooth immersion, and it's also a topological embedding, because the image of U inside M under inclusion is U itself, which is open. So anyway, once you guys get to the point of topology, once you get to the subspace topology in your topology course, this would be like it would just be so like obvious. It would be silly. It's hard. Anyway, I'll shut up. Next up here. Example 2, you can look at the inclusion map, the jth inclusion of, let's say, the jth manifold being included into the Cartesian product manifold of M1 through AK. And here the inclusion map works like so. Ij of Q is equal to P1 Pj minus 1 Q Pj plus 1 Pk. There you go. You might ask what the P's are. The answer is whatever you want them to be. This isn't just one map that's a smooth embedding. It's like an infinity of them. Any choice of the complementary points to Q gives you a smooth immersion of Mj into this Cartesian product of manifolds. Okay, so you do that. And then part C, he gives an example. It says problem 412 shows that the map from R2 to R3 by example 4.2 descends to a smooth embedding of the torus, but I'm not going to get into that right now. So let's see here. Now, a counterexample is given here by example 14. We should write that out. I think it's maybe it's this thing I was just talking about up here. Let's find out here. So example 4.18, he gives us a smooth, he says it's a smooth topological embedding. And so here it says gamma from the reals to R2 given by gamma of t equals to t cubed comma 0. He says that's a smooth map and it's a topological embedding, but it's not a smooth embedding. All right. let's understand for ourselves, why is this not a smooth embedding? So the fact that it's a what's the word? Homeomorphism, the fact that it's a homeomorphism onto its image is pretty obvious. Like, so what is the image? The image is just the x-axis in R2, right? So yeah, the real line is homeomorphic to the x-axis. And this mapping is invertible. Its inverse is the cube root. They're both continuous. All right, great. So why is it not a smooth embedding of the reals into R2? So what's, yeah?
Well, do we have to consider the inversion by less than?
No, just focus on the smooth immersion thing. Like what would it, we need the rank of the differential, right? So the rank of the differential for a curve we can judge by its velocity vector, right? So like what's gamma prime? Gamma prime of t is what? It would be, you could identify it with what, like 3t squared comma 0, right? That's the Jacobian matrix essentially here. Is that always rank 1?
Keep taking derivatives.
No. Is this rank 1?
Yes.
For t not equal to 0, you're right. But what about t equal to 0? See? So right there, the rank of the differential is 0. But the dimension of this guy is 1. We'd have to have rank 1 everywhere for this to be a smooth immersion. But it's not, so it's not. So this is an example of a thing that's a topological embedding, but nevertheless not a smooth embedding. And I do think that this is related to that other thing we talked about before, right? Like the whole fact that like the cube versus the cube root and the derivative of the cube root having the vertical tangent. I think it's part of that same bag of ideas, if you will. So another example we should look at here is the figure 8 curve. So these are important examples, and he gets a lot of mileage out of these, both in this chapter and also the next. So let's just camp out here for a second, make sure we understand it. Example 4.19, so-called figure 8 curve. The parameterization of this guy, beta, from minus pi to R2 is given by beta of t is sine 2t and then sine t. All right. He says the image looks like a figure 8 in the plane. Let me draw the picture up here. So what goes on is, let's see if I can draw this with some color coding maybe. All right, so like suppose this is minus pi, this is pi, here's 0 in the middle. Let me attempt some color coding here. So I'll do like, and this is not quite, I'm not saying this is exactly it, but something like this. All right, like I'm totally fuzzy exactly where the end of the orange is and the start of the red and the green I'm about to draw is. But like, maybe it's this one. I'm actually not sure if this is right. I mean, we could figure this out if my picture is like bogus or not, 50-50. all right? 50-50. Like that.
Oh, the red on the two negative on the bottom.
Oh, yes, thank you. That would have bothered me immensely if I came back and didn't do this. All right, so am I right? Yeah. Let's think about it right quick. What if we have minus, like, put in like minus pi? What happens? Well, they're both 0. That doesn't help. How about like a little bit before, like, oh, like minus 3/4 pi maybe? Minus 3/4 pi. Minus 3/4 pi. Oh, minus 3?
I mean, it's closer to pi.
Okay, what's sine of 3?
Let me pull mine.
He has no idea.
That's why I did 3/4.
Infinite series calculation.
All right, yeah. Infinite series calculation. You guys are killing me. How about, so if we did 3/4 minus 3/4 pi, my life will be easier if I just draw. Here's sine. And here's, there's sine 2t. Here's sine t. All right, so if we're, and I regret not, dummy. All right, I'll fix it. No, that can't fix it. Can't be fixed like that. Oh, man. I wanted minus pi to pi.
Looks like it's -1 for sine of 2t.
Dang it. Fine. There's your minus pi. There's your pi. All right, so maybe we can figure it out from this one. So sine, yeah, this should be enough, right? So sine of almost minus pi is negative. Ah!
Good one, good one.
There we go. Now we've got sine of minus pi has got a negative y value, right? But a positive x value, because sine of 2t is like, you know, anyway. And then the green one would be closer to pi. Closer to pi, sine of pi is positive, so yeah, positive. Okay, great. All right, anyway. Sorry. Like I said, 50-50. All right, so the point here, let's see here. So we could calculate the, he says it's easy to see it's an injective smooth immersion because beta prime never vanishes, right? You can calculate the velocity vector, right? And you do so because we're working in R2, we can identify the derivation with the point, which has the derivation components as its, you know. So we can literally make the calc 3 kind of, you know, calculation, differentiate, and then you can check that neither of those, well, when one of those is 0, the other one's not, right? They're never both 0 from minus pi to pi. So that makes this a smooth immersion, I believe. Now, it's a smooth immersion because beta prime t never vanishes, but it's not a topological embedding because it's, now why is it, oh, this is actually interesting. Why is it not a topological embedding? So it's a smooth immersion. However, not a smooth embedding. Since not beta, not a homeomorphism. Now homeomorphisms, right, onto the subspace topology. All right, so like, I need to use some topology you guys don't have yet. But, one of the interesting theorems we have in topology is that the continuous image of a, well, certainly if I have a homeomorphism and I map a compact set, then the image will also be compact, and vice versa. So like the inverse image of a compact set is compact. What are compact subsets of the reals? Compact subsets of the reals are just closed intervals. All right, so like that's a compact subset of the reals. Well, at least that's one kind. Anyway, so certainly this is not compact. All right, it's like an open set is not. So compact means in the context of Rn or metric spaces, compact means closed and bounded. This is the Heine-Borel theorem. All right, and so open interval from minus pi to pi is not compact. However, the set over there, the figure 8, is compact in R2 because it's a closed curve, right? Like the complement of that curve is basically the whole plane with like a figure 8 cut out of it. And every point in there is an interior point. You can put a little ball around it, which makes it open in the metric topology of R2, which you guys almost know about. And so therefore, oh, good. So like the figure 8, in fact, any curve is usually closed if it doesn't have, I guess depending on endpoints, I might not be able to say that. But in this one, this is a closed curve. Because the point that you don't get to with these guys, it's already in the orange part. So the figure 8's compact, but the domain is not. Therefore, it's not a homeomorphism, because homeomorphism preserves compactness of sets. Compactness is a topological data. It has to be preserved. Homeomorphism preserves all of the topological data from one topological space to another. Like that's something you guys should be, looking towards. So there you go. Smooth immersion, but not smooth embedding. And then the other one he gives an example of is the dense curve on a torus. So T2 is the S I can't draw. I'll just do it like this. I'm gonna start doing this, S1. Maybe I'll just go back to my other S. I don't know. It's not right. Anyway, subset of C2, right? And the mapping that he gives here, gamma of T, is e to the 2 pi I T and e to the 2 pi I alpha T. All right? And basically alpha is an element of the reals, but it's not rational. So for example, you could take alpha equal to e if you want to have a specific thing here. And he's got about a paragraph where he argues using Dirichlet's approximation theorem and some other things that this curve densely covers the torus. Dense is another thing you'll learn in topology that has a meaning as well. It's a technical topological term. But what that really means, if you just want to kind of picture it, is that this thing just keeps winding round and round and round the torus, but it never gets back where it started again. So if you were to kind of look at that as a picture, it's like every point on the torus is covered. That's not quite true. But every point on the torus has another point infinitely close to it, which has been covered. That's the density. Something like that. So that, and you can check that gamma prime of T is never equal to 0. So, and not just that, I think, well, yeah, that. So it's a smooth immersion, I believe, of, well, the real line onto the torus. So it's kind of weird, right? So I think it's weird. It means like you can basically take the real line and essentially cover the whole torus with it. Yeah. So it means, so like, I don't know, it's just, to me it's weird. All right, so moving on here. Let's see here what I want to talk about. What do I want to talk about? Keep the time in mind here. All right. We'll skip ahead a bit here to chapter 5. So we will talk about different kinds of submanifolds. What is a submanifold? A manifold, which is a subset of a manifold, is a pretty good guess. The question is, in what sense? Right? Like,
that it preserves X properties.
such that it preserves X properties. I like that answer. So there are different kinds of submanifolds that you can talk about. All right. So there are what are called embedded submanifolds. There are also what are called immersed submanifolds. There are weakly immersed submanifolds. There are properly embedded submanifolds. There are, I think that's it. But so comfortably embedded. I like that. That's funny. Okay, so here we go. So an embedded submanifold of M, all right, is a subset. You got that right, Jeff. Subset of M. Is subset, which is a manifold. Jeff's like, that's what I said.
This is what I said.
Without boundary. In the subspace topology. Right. And it's endowed with a smooth structure with respect to the inclusion map is a smooth embedding. In particular, so what we have is like, S included into M is a smooth embedding. In other words, I have been using this, I really want to put the dot on it, Yoda map. It's technically IOTA. That's what it is. That's a smooth embedding. Now, sometimes embedded submanifolds are also called regular submanifolds by some authors. All right? So that's definition. Let's see here. The dimension of M minus the dimension of S is called the codimension. The codimension of S is equal to the dimension of M minus the dimension of S. That's the codimension, right? And usually we call the manifold M, which contains S, the ambient manifold for S. He says an embedded hypersurface is an embedded submanifold of codimension 1.